the recording on. I think we've got her. Let's get these slides. Getting everybody seeing the slides. Everybody seeing? Anybody seeing the slides? Somebody tell me.
Yep, see them.
Okay, great. All right, so we'll get going then. Thank you. Remind you just to keep your phone muted. Marion and Liz will be monitoring the chat window as well as myself for questions that we will take at the end. I want to welcome you. Thank you for taking your time out to hear this morning's update on the Complex Ratings Project. I want to introduce the project team members. We have Marion Demansky from the Central Midwest Water Science Center and Liz Heel from the Lower Mississippi Gulf Water Science Center. My name is Bob Holmes. I'm with the Earth Systems Process Division, and I'm the project manager. So the issue that got this all started a number of years ago when I was with the Office of Surface Water was the issue of hysteresis or loops. And you can see here that I've got a demonstration here. This is a numerical exercise I did a number of years ago when we first started experimenting with this. Because we were originally, we got talking, people were thinking this was only happening with streams with floodplains, storage going in and out of the floodplains. So we set out to look at kind of the causes, looking at the history, looking at the literature search. And this little numerical exercise just is something I've used to demonstrate to the water science centers in the past that you can have hysteresis even with a very compact non-floodplain channel. And so if you look here in the green, we've got a slope of a foot per mile, and the blue is a slope of 5 feet per mile. So you can see the lower gradient slopes are more susceptible to loops than the higher gradient slopes. But then if you look at the same 5 feet per mile in red, that's a system where I let the hydrograph as it entered this 1,000-foot wide rectangular channel in this numerical exercise, I let the flood hydrograph be a little more unsteady, and you can see that even at that 5 foot per mile, we get this loop effect. So that's what the issue started driving this around the 2013-2014 timeframe. Just a few demonstrations of loops. This is Vicksburg on the Mississippi River, and we have a slope here of about a half a foot per mile. And you can see that basically that loop width is about 300,000 CFS there near the top. And that's about 18% of the flow at that point. I'm getting a little feedback. If everybody would mute their phone, please, hearing some feedback. I'm sure it's disturbing to others. It just doesn't happen on those very real low gradient sites, half a foot per mile. This is some data from a site in South Carolina where we've got 31.5 foot per mile. And you can see here that the loop is, basically 42% of the discharge at the middle part of the rating curve. Just so you don't think this is an East Coast problem or an Eastern United States problem, this is from a site in Arizona where we were looking at about 23%. Again, a 35.2 foot per mile. You will note at the bottom that over half the StreamStats database sites, that's 14,000 sites, have slopes that are less than 35.2 foot per mile. So this is a potential to be a large problem. So the goal we set forth in 2014, 2015 was to develop and test a method to provide a dynamic rating that will account for complexity in ratings. So we have some methods out there. You have, if you can use slope stations, if you got 2 gauges, there's some other things, the Boyer method, different things that people use. Obviously, index velocity has become a very popular alternative, but we wanted to see if we could add to this the tools, if we could find something that worked a little better using a single discharge station. So if we look at this, when I was looking, and again, this is a differential equation, so don't let it scare you. I want to spend just a moment of time here just to kind of talk a little bit about it to set the framework of what we ended up using in this project. As we stood up the reorganization of the USGS, or at least the water mission area, this became a project in January of 2020 based on what we had done in the Office of Surface Water in previous years, and really jump-started this in getting to the point where we are now. But before we talk about exactly what we've done, I want to spend just a moment thinking about this. This is the Manning equation. Many of you know this. The discharge is related and a function of the roughness, that's the N. The channel geometry, that's the A and the R there. And then this friction slope is the S sub F. The typical single valued rating curve at the bottom left from the Burbus River near Highgate, Missouri, you can see it's a well-behaved rating curve from those discharge measurements. And when you have a well-behaved rating curve, hello?
Hello?
Getting some feedback. Are you guys still there? Okay. Marion, can you still hear me?
Yeah, I can still hear you, Bob.
I can hear you, Bob.
Okay. Okay. Please mute your phones. The friction slope is, we can assume that that's approximately equal to bed slope. So it makes it a nice, what we call the uniform flow assumption. For the most part, we can't assume that. The friction slope is much more complicated. And this is something called the one-dimensional St. Venant momentum equation. And I want to introduce this just to kind of give you an idea of what factors into this friction slope. Not only do you have this bed slope, but you have something called the pressure term, which basically, don't let this scare you. All this says, the depth, which is y, is varying in the downstream direction, and that's x. And then we have this convective acceleration term, which says that the velocity is varying in the downstream direction x. We call that convective acceleration, and you can think of it as the contraction and expansion of the channel. And so as it contracts, the velocity increases as you move downstream. As it expands, the velocity decreases. And that's what this term's all about here. And then this last term here is the what we call the local acceleration. That's due to the unsteadiness of the flow. If you have a flood wave moving through, that velocity at the location of the stream gauge, how that varies with respect to time, that's called this local acceleration.
Now John just published another paper that says,
okay, so can somebody mute their phone, please? I can't tell who that is, but somebody's got a recording playing. All right, so as we look through this, you know, when I was working on this early on, I found this paper from Danny Fred back in 1973, where he had developed this thing called a dynamic model. And he used these one-dimensional St. Venant equations. You've seen this one here before. That's what the previous slide was about. That was the conservation of momentum. This is the conservation of mass. And the thing I want you to take home here is these equations have embedded in them variations of discharge, depth, and velocity with space. What we had to do, or what Danny Fred did, was he got some simplifying assumptions that made it possible to use data from a single location at a stream gauge and got rid of these spatial dimensions. And so that's what, I'm not going to go into the details of the assumptions. That will be in the final report that we issued at the end of the fiscal year. But just keep that in mind. We're getting rid of this. This whole method is based on having data at one location. And that method requires cross-section geometry and roughness at a representative cross-section near the stream gauge, and requires a time series of stage at that location. And then the last item it requires is data from one flood hydrograph where you measure the characteristics of the flow. You basically look at how does the timing of that flood wave occur from when the onset of the flood wave at the stream gauge. What is the time differential between that flow? What is that magnitude of the flow at the base flow event? What's the stage and magnitude of the flow at that base flow? And then what's the magnitude and stage of the flow at the peak, and the difference between the two? That's all the information you need to make this method work. And what we do then is we input that into this dynamic model, and no additional discharge measurements are required. This is not a rating curve like we think of it in terms of the typical water science center, where you make these measurements, you get a rating curve, and then you make ensuing measurements and you shift that rating curve. None of that is required in this method. Danny Fred assessment in a follow-on paper that was published in 1975, where he looked at the Mississippi River at Tarbert Landing. Some of you may have known this as Red River Landing. It's basically the same site. The Corps calls it one thing, the Weather Service calls it another. There's a few miles difference between Tarbert and Red River Landing. But essentially, what this shown in his experiment was, in the circles, the dots here, those are actual observed discharge measurements. In the straight line, the linear line here is this dynamic model, and you can see that it fits the data very well. At the top here is not a rating curve in the sense of he used a rating curve. I want to reiterate that. He's just basically showing how well this model picks up these loops. And in this presentation, we're going to show you how the loops work in the model that we're working on here. So I didn't want to just take the word for Danny Fred from work he had done in the early 70s. So the Office of Surface Water commissioned a little bit of work here when we worked with the Missouri Water Science Center and targeted a flood in 2015. And originally, when Missouri agreed to help me with this, we thought, well, this would be probably a 10, 15 day effort over a flood hydrograph. This ended up being 2 months worth of time, because as the floods got going, we kept getting ensuing rainstorms higher up in the basin. This flood lasted for a couple months. And you can see we've got 39 measurements here to use as our test data. What I then took was a flood event from a decade earlier and built the dynamic rating model. I got the channel geometry, I made an estimate of the roughness, and then I had that flood hydrograph from a decade earlier and built all the things I needed for the model and then ran it. And so I want to stress to you that the model does not use the data, the observed data, and you'll see these, the green dots are the discharge measurements, doesn't use that to make this estimate. So in the blue, you have what the dynamic model or the FRED model computed. In red is what the Water Science Center has as published final data. And you can see that there's really good agreement. You can see that the N value varied through space. I had a stage variant for the roughness based on some. I had enough data there at an ensuing gauge to get slopes and back calculate N values for different discharge measurements. So I had a pretty good idea what the roughness was. And so you can see from the statistics, the metrics, that basically the root mean square error here is about 23,000 CFS for the difference between the measurements and the USGS a computed flow that the Water Science Center computed off of the rating curves. And then you can see the difference. The RMSE is about 21,000 for the FRED model versus those observed. So we were very encouraged by this. And so this, proved to be kind of the tipping point to try to pursue this further. Of course, then we hit the reorganization, but fortunately, it was decided to fund this as a project that started this past January. The problem is that this method from FRED was based on compact geometry. So if you look at the left here, you can see what we mean by that. You can see this nice trapezoidal channel is a nice compact geometry, and that's based on the assumptions he made in order to get the model to work, to get rid of the spatial term in the St. Venant equations. What we needed to do was develop a new algorithm that would expand this method to get into non-compact geometry situations, essentially floodplains. And here on the right, you see that we've got a schematic here of what we're talking about. You've not only got the trapezoidal main channel, but you've got this floodplain. So you have to do some different things, and we've been experimenting and developing the algorithm for that. And Marion's done the lion's share of that work in developing the algorithm, and the code development began in January 2020. Now, concurrent with that, we made an appeal to the field in January 2020, and many of you listened to that appeal and sent us test sites because we wanted real data. Not only were we testing this against some numerical data that we've ran using full-blown 1D unsteady flow models of channels that we can construct and help us with the algorithm development, but we also wanted field data. And so we sent out an appeal in January 2020 looking for sites with the presence of a complex rating. But oh yeah, we also, not only do they need to have complex rating, but we need to have reliable Q data for the truth, and then we need channel geometry to back that up. So I'm going to let Liz Heel talk for a bit here and talk about how we get to that point once we got these sites in from you and what she did to reduce that data. Liz?
So channel geometry is really important to this model. To develop this geometry, ideally, we need ADCP measurements with GPS data. And if we don't have GPS data, we can use an approximate location based on notes from the field office. But if neither is available, we generally can't use the site for testing. We chose 14 out of 27 sites submitted, and some of them were not used just because we couldn't get a good location data. So it is possible to use a DEM-derived version, but there's no elevation data below the water surface, and so we would be estimating the channel shape. So channel geometry based on these ADCP measurements is essential. And this site on the Tittabawassee River is a good example of an almost perfect match between the ADCP transect and the DEM-derived version. I used the measurement output from Wind River, sometimes River Surveyor, and imported that information into AreaComp2. And then I took the GPS data and I drew a cross section in HEC-RAS on the DEM. Can show them the next slide. And so this is the final version for this river. So the graph on the left shows both cross section. The ADCP version is in blue and the DEM version is in orange. And then the graph on the right side is the final cross section. So you can see how well they align there, and that this one was just cake. It was great. We used the DEM just to extend that floodplain on either side of the channel. And next slide. And these are the final 14 sites that we chose out of the 27 to use.
Okay, so you can see that the location of the test sites we had, as Liz mentioned, it was a tall task in terms of trying to find sites that had complex ratings, but also had good truth data. So at this point, we want to talk a little bit about the results we've gotten so far, and Marion is going to take that part.
Thanks, Bob. Okay, so the next series of slides, I'm going to show the DynRat computer discharge as a time series. Along with that computer time series, there's going to be Water Science Center computer discharge or the rated discharge, as well as there's going to be another plot with stage time series. And the Water Science Center computer discharge and the stage Water Science Center computer discharge and stage time series came from either NWIS or Aquarius. And on most of the slides, I'm going to show a root mean squared error, and that's going to be the DynRat computer discharge compared with the Water Science Center computer discharge. And that's unlike the root mean squared error that Bob showed for the St. Louis site, which was the DynRat computer discharge with compared against field measurements. And if you're curious, have all of the results on code.usgs.gov in a repository. They're all in Jupyter notebooks. And if you go to that website, there's links to the notebooks, and the notebooks are all rendered so you could see the all of the plots. And that's an internal website. So if once you sign into code.usgs.gov with your USGS ID, you'll be able to view that. So next slide, please. So this is the Connecticut River. So, this is definitely a very encouraging and promising result here for DynRat. It's very similar to the Water Science Center computer discharge. If you look at the beginning and at the end of this time period, we have field measurements that DynRat is capturing well. Also at the peak of the time period, there's a couple field measurements that DynRat is computing very well. Next slide, please. So the Meherrin River. So DynRat does well on the rising limb as far as when we compare it to the field measurement. It's a little off at the peak and on the falling limb. I'd like to point out, to bring up again that one of the major factors in how the performance of DynRat is the channel geometry. So for this site, for instance, I would, after comparing it to several events, I would go and if the performance was similar, I would go and look at the channel geometry to make sure that it's representative. The channel cross section is representative of the reach that the measurement cross section is in. Next slide, please. Another Meherrin River site, in a similar case. Well, DynRat does well on the rising limb, is a bit off on the falling limb. And again, I'd revisit the channel geometry in this case. But overall, the shape of the DynRat hydrograph is very similar to the Water Science Center computer discharge, and still very promising results. Next slide, please. Tug Fork at Kermit, West Virginia. This one is a great example of the DynRat performance. We're definitely nailing that the field measurement at the beginning of the time period, and capturing the field measurements very well on the rising limb, a bit off on the falling limb. But overall, DynRat does a very good job here. And again, the shape of the hydrograph is pretty good when compared to the Water Science Center computed hydrograph. Next slide, please. So if you notice, there's not a root mean squared error computed for this. I mean, it's obvious that the DynRat computed discharge is lower than the Water Science Center computed discharge, so we don't really need to quantify that. But I'd like to point out that, well, for this site anyway, I just threw in the cross-section geometry, put in some typical roughness values, and ran the computation. It didn't really take too much for me to at least get where the field measurements are. So when I got the field measurements, I was satisfied, and then moved on to the next site. So next slide, please. The Patoka River, Jasper, Indiana. I'm not very familiar with the flow conditions at the site, so it's hard for me to say what's exactly happening here, especially with the smaller peak at the beginning. That's just before the peak of the time period. But I'd like to point out that DynRat does capture something there. And it looks pretty well when compared to the field measurements. Through the larger event, the larger peak there, and although it's a bit above the field measurement in the later part of the time series, overall it does a pretty good job. And I think that again, I would revisit the cross section geometry here for this site. Next slide, please. Tittabawassee. This is another great example, both at near the peak of the hydrograph and on the falling limb. When compared to the field measurements, DynRat captured those very well. And the shape of the hydrograph is pretty similar to the Water Science Center computed hydrograph. Next slide, please. So Blackwater River at Blue Lick, Missouri. This is another site that I'm not really familiar with any of the flow conditions at any of these sites, but it's hard for me to say why. We have that dip between the smaller peak at the beginning of the major event there, and then the peak of the time period. Again, another site where I would go and look at the cross-section geometry. But other than that, I mean, the overall shape is still very encouraging for DynRat. Next slide, please. Calcasieu River near Kinder, Louisiana. Now here, there's only one field measurement within this time period, but we do have 3 events in the field measurement that is within the time period. DynRat does very well with, same thing with the Water Science Center computer discharge. But overall, the DynRat does, it's doing a good job with this site, and how the shape of the hydrograph is again very similar to the computer discharge from the Water Science Center. Next slide, please. Okay, so for the next few slides, we're going to show the stage discharge plot for a few sites here, and this is just to demonstrate that the hysteresis in the hydrograph and the non one-to-one relationship between stage and discharge for the computed time series. You know, we're basically going to show loops in the rating or loops in the hydrograph or in the relation. And again, I'd like to reiterate that there is no stage discharge value that's directly forced between for computing the DynRat time series. The only thing what DynRat needs is cross-section geometry with roughness values, some typical flood characteristics, and an observed stage time series, as well as a previously computed discharge, and all those things go into the computation of the discharge at the next time step. Next slide, please. So Tug Fork at Kermit, West Virginia. So this is, you know, we have the loop in the relation here, and we have what we would expect, where the rising limb on the larger event, you know, is on the lower part of that loop there, and then the falling limb is in the higher part. So there's the higher stage values. And if you notice, both events in this time period have their own distinct path around the loop. So the smaller event, the loop of the smaller event is, you know, within the loop of the larger event. Next slide, please. Tittabawassee River again. So again, you know, we have the rising limb is on the lower part of the stage values, and then the falling limb is on the higher part. And I'd like to point out, like around 12,000 CFS or so, there's almost a distinct break in the slope of the relation here. And that's, you know, a demonstration of the effect that the cross-section geometry has on the relation, whereas the you know, the stage changes, and or as the cross-section properties changes with stage, it has a pretty big impact on how the relation goes through time. Also, if you know, it's hard to see in this plot, but if you look at the beginning of the time series, there's a smaller event here. And that shows up in the lower discharge region of the relation. And if you notice how the path of the stage discharge for that event doesn't follow the same path as the larger event. And as Bob mentioned before, the rate of change of stage does have an impact on how how big a loop is, or how, you know, and the hysteresis of the stage discharge relation. Next slide, please. So the Calcasieu River again. You know, here we have another pretty even more distinct break in the relation around 5,000 CFS. And you know, all three events have their own distinct path around that loop. So we have the larger event is with the loops of the smaller events are within the larger event there. So next slide, please.
Thanks, Marion. I just want to stress, in all these tests, we did not use any of the discharge measurements or information other than the stage from the actual event that we were testing against, or we were running the DynRat model against. All that information came from a previous flood event where we had to have the flood wave information. And so, you know, don't think that we did this by calibrating against the discharge measurements that were made during those events. They weren't used at all. It's just it's very encouraging to see the kind of results we're getting from this. And it appears to, and it just occurs to me that we need to put out a new call to the field. And I think we built this model based on the fact that we're trying to address loops, but I think this could be used as a dynamic rating method for even non-complex rating sites. So we've got a new call we're putting out. We think because it can perform pretty well against non-complex sites, we'd like to get some of that kind of information. So we're looking for sites with standard rating curves with excellent truth data. You've got either a lot of observations over flood events, so there's a lot of discharge measurements, or you've got a rock solid rating. We'd like to test the model against those. Particularly, we'd like to see, you notice on our map, we've got, all of our sites are in the eastern part of the United States. We'd like to see the western half represented. Plus, we'd also like to see things from Hawaii and Alaska as well. Now, we only have so much time available. This project scheduled in September of next year. And so we've been running this since January. So we're 12 months into this effort. We've got basically another 9 months to wrap it up and have a final report. We're not going to have a final operational process out there. We're proving the method. We're writing the algorithm code, et cetera. It'll be a follow-on project that makes this operational for the water mission area. But we would like to kind of do a force multiplier here. We know that there are code savvy personnel out in the water science centers. So we're offering this up to do some direct testing. But it does require some, as I said, some savvy from people. We're not going to give you a package for DynRat that's able to it's not an executable where you can just plug it in and go with it. It's not got a GUI on it. You have to use Jupyter Notebooks directly with the DynRat API to use it, so it requires some programming knowledge. But we want to make that offer out there. I'd promised Chad Wagner that we would do that back at the last quarterly project review for this thing. He'd suggested, there were some centers he knew of that might be interested, might have the capabilities to do that. So we want to definitely make that offer to you all. So at this point, I'll give you the contact information. If you got project questions, the theory of this, where we're going with this, et cetera, you can contact me. If you've got some new test sites that you want to propose that have that standard rating and you want us to do the testing, we may not be, if we have 200 sites given to us, I'm not sure we'll get to all 200, but we'll do as best we can. And then if you've got if you think that you've got the people, the horses to do the direct testing, we encourage you, and Marion's the connection there. So for proposed new test sites, you can email Liz. You can see for the direct testing, you got Marion's email address. So at this point, we'll open it up for questions and see kind of what you think. We're very encouraged. I think this is going to be a very very nice package for the field to use, especially in some of these complex rating sites, or who knows, maybe in some standard sites as well. So I'm going to go to where I can see the chat and see if I can get that up and see things here. So I don't know, or do we have any questions in the chat window? Not seeing any. So do we have any questions at this point?
Bob, this is Janice. Could you go back to your slide where you showed the really cool, early on when you showed all the detailed measurements that you did, that you presented, and you did the root mean squared between the measured discharges and the actual, it's down after that. Yeah. Yep. You talked a little bit about the root mean squared error. Could you talk a little bit about the absolute difference that you have there between the two? And yeah. Give a little more insight on what those numbers actually mean.
So the root mean square error is basically the difference between the model data or the Water Science Center computed data and the actual observed data in green. So we're considering the green being the truth, and the other things being a model, essentially. Even the USGS rating is the model. So that's the root mean square error. The absolute percent difference is basically the absolute value. We're not testing bias here. So it's basically the absolute value of the different, it's the percent difference between the modeled value, either a USGS rated by the Water Science Center or DynRat difference. So obviously, you can see that the USGS rating is 3.41%. That's, they've rated this site for as good data. It basically proves that we're well under 5% here. But DynRat, not using any of that green observed data, used data from a previous flood event, it's almost as good. and that the only intervention I did is assign an N value.
Okay.
That's it. And so the DynRat model, just running it, I mean, you get the cross-section geometry, so we've got a good cross-section, so you generate a table of cross-section properties of stage versus cross-sectional area, hydraulic radius, wetted perimeter, those kind of things. And I've got an N value, and then I've got characteristics of a flood wave that I did from I think the 2011 flood. No, I guess it was on before that. It was a flood back in like 2005 or something like that. And essentially that's it. So then I just run the model, and this is the result you get, which was the original result we got to encourage us to pursue this when we were doing this as part of the Office of Surface Water.
Okay. Well, thanks for the explanation.
Thanks, Janice. Other questions?
There's a question from Robert Mason on there. How useful is the program for extrapolation above measured flows?
Well, we again, the method doesn't well, for example, here at St. Louis, we took a flood event that was lower in magnitude than the 700,000 for this. So in essence, the method is blind to what we've got for measurements. The only thing that's kind of the built-in memory is how does a flood wave behave, and the way that it's constructed is it looks at that flood wave and says, what is the ratio of the slope of the flood wave versus the bed slope? That's essentially what we're extracting from that information. And so as long as you're characterizing the flood wave properly in the sense that it's capturing what the slope of that long flood wave is versus the slope of the bed, it's blind to kind of anything else. So it's not, like a Water Science Center rating curve. We'd have a policy in the old Office of Surface Water that you don't extrapolate that rating more than 2 times the highest discharge measurement. We don't have that rule in this DynRat because it's basically taking a characteristic of the way the flood wave behaves. And as long as the flood wave behaves at that high flow event, similar to what it did at the flood wave that you used to build the model, it doesn't care. So I'm not sure I'm answering your question exactly, Robert, but in this particular case at St. Louis, we had a flood wave that was only 400,000 CFS. Here we've got a flood wave that's 700,000 in terms of the peak, and the model performed really well. The other events that we used in the testing, I'd have to go back and confirm with where we got the information on the flood wave for the Meherrin and the Connecticut River, et cetera. But I'm assuming that those flood waves are similar. I don't know that these were I don't know if this is a massive flood on Meherrin. 25,000. Is that a massive flood? Is that a very rare flood? I don't know. We'd have to go back and look at that. Okay, any other questions? Trying to look here at the chat window. Well, again, this was just sort of a technical update. I'm hoping that you guys will take our offer seriously and send us some information. We'd like to test this some more. We'd like you to test it if you got people to do it, and we'll make that available to you. I'll pause a minute. It seems like, Robert, I see your light is buzzing. Were you wanting to ask some follow-on question?
Not really. As I understand this, Bob, if the cross section and the slope are more or less consistent, you're saying that we can I used the word extrapolate, but we can extend a looped rating beyond the measurements that we have.
Yeah, I mean, again, it's all about so if the shape of this flood wave, I've got the Meherrin River up here. So you've got, we would extract on a previous flood, not this one, we would have extracted the value of the stage and discharge prior to the onset. Are you guys still seeing my cursor? Can you see my cursor?
Yes. Yes.
Okay. So the information, we would look back in time and we would, if we were starting from scratch, and this method works, here's what I see as a scenario. a water science center would go out and they would say for this, let's say that this was a new site, Meherrin River. They would go out and say, let's look for the next flood wave that's going to happen, or next flood's going to happen. And let's make sure we understand what the discharge and the stage is prior to the onset of the flood. So they would have a value for stage and discharge down here where my cursor is. Then they would monitor this over a particular flood. And the thing that they would really concentrate on is getting the stage and the discharge at the very crest or the very peak of the flood. From those two pieces of information, and then doing a cross-section survey and understanding from topographic maps or other means what the actual bed slope is, that information is all they need to run this model. And so, as long as this is the data they selected to collect the detailed information of the peak and the base flow values, as long as that's a representative flood wave, the characteristic flood wave, this model should work well, at least in what we're seeing. And so, in this particular site here, Marion went back in time, used another flood, took and got the characteristics of that flood wave, what the peak was, what the base flow was, what the timing between the two is, and that's all the information used, other than the geometry of the cross section and the roughness. This you can't think of this as a standard rating curve business. This is not. You don't. I mean, yeah, obviously we're still going to collect discharge data to make sure the model's still working right, but this thing could cut down on the number of measurements we make and increase the accuracy of the information that we're modeling, or the output of the unit value discharge. And you can see in some cases we actually, I think, do better in parts of the hydrograph than what the Water Science Center computed discharge is. Other places we're not doing as well. So we're not really sure exactly why that's so. Here, both the Water Science Center and the DynRat model are kind of missing it, both total peak and missing the base, the recession. Here both are doing really well. I think DynRat, without even having these discharge measurements here at Tug Fork, are actually doing better than the Water Science Center computed discharge. And then we're not doing as well on the recession, but we're still not too bad. Again, this is not an indictment in any water science centers. I'm not saying they're doing a good, bad, or indifferent. They've got information that we don't necessarily have. And so this is running the model sort of blind. All we've got is the geometry data and the time series information in a previous flood event that we use. So this presentation is being recorded as well. So I know there were some people that weren't able to attend. So you can go back over this if you like, and I'll make these slides available as well.
I didn't say it, Bob, but it's been a super presentation. Thanks to you, Liz and Marion, for putting it together.
You bet.
Bob, this is Casey. Just a quick question. So when it's not matching discharge measurements, well, are pretty much the two knobs to look at? That maybe one, we don't have a good cross section, or two, maybe our assumption about roughness is wrong. Are those the two, or?
Yeah, so there's actually a third knob. So there's the cross section data. That's the most sensitive of it. It's sort of like a 2D flow model. The cross section or the topography of the information that you feed the model is more sensitive even than the roughness, unlike the 1D model, which is usually the 1D unsteady models, roughness plays a bigger sensitive role. So that's a major role, is making sure the cross section's right. The next thing is making sure that you get the roughness. And then the third one is this whole thing about the flood wave characteristic. So we can play around with that, although that's not as sensitive as the geometry or the roughness. Marion, would you want to comment on that? I mean, my sense is that of those three, the flood wave, the slope of the flood wave versus the bed slope are not as sensitive as the other two. Marion, do you feel differently?
No, yeah, I agree. It's definitely the cross-section geometry affects, that has a huge effect on the actual shape of that, the stage discharge relation, and then the roughness pretty much just moves almost translates that. So, and then the flood the flood wave characteristic has the least effect on the results.
Bob, we have a comment and another question on chat. It's so Catherine Chase says that it appears from some of the examples that a higher flood wave might behave differently than lower recorded flood waves, as in loops are nested. And then, let's see. And then the question is from Joshua, is it possible for DynRat to pick up on backwater with only slope for one location?
So let me take the first one first, and Catherine, that's really good. Mary was making this point, but let me just really drive it home. Here's Tug Fork at Kermit, and the first flood hydrograph or first flood wave that moves through is right here, and you can see that reflected in the darker. Some of you may be colorblind, so I apologize. I know our developer of this particular code, Marion, is colorblind, so hats off for him to putting this really cool visualization together. But the dark red here is the rising limb, the lighter red, the pink, is the falling limb, and you can see it's captured pretty well here. And that's a bigger loop than right out here with this next flood that moves through. You can see that the rate of rise is faster, the unsteadiness term. And I had that on the second or third slide where I really showed you the 5 foot per mile, the two comparison of one that's more unsteady than the other one. And the loop magnitude of the width of this loop is pretty dramatic here, in the sense that for this one that rises faster, the loop is wider. You can see this one's a lot more gradual rise, and the loop is smaller. So in the data, in the numerical estimation of these floods from DynRat, you kind of see that playing out. So that's the first thing, is that to address Kathy's. And Liz, can you read the second question? I apologize.
Yep, the second question is from Jeff Woods. How is storage dealt with? Is that incorporated into the flood wave discussion you just provided?
Yeah, so storage would be built in the sense that it's built into the model dynamics. And so one thing we didn't touch on, you may be getting to this, if this is an approximate one-dimensional model, we can approximate the flow as one-dimensional. I think this method is going to work really well, even with floodplains as it goes in. It's if that transition to the floodplain, and typically we get that working well on low gradient streams, where that transition to floodplain flow is not as dramatic as something that's higher gradient. So if you can approximate that, it's as a gradually varied flow that spreads out onto the floodplain and doesn't wholly violate, the 1D assumption, I think it's going to work fine. Where we're going to break down in this model, I think, and we are going to try to come up with some rules of thumb here as we issue the report, is where you get into a highly two-dimensional situation where you've got this highly rapidly varied flow. If your staged data is on the upstream side of the bridge, and you've got this highly two-dimensional situation of constriction, and maybe you've put that represented cross-section on the upstream side, I can see where that would bias. The model would not do well to represent what's going on there in terms of flow coming into and out of the floodplain. It doesn't address the storage issue you're talking about, just the simple sense of it. The flow is not one-dimensional. It's not along the streamwise coordinate of the flow predominantly. And so I think the model is going to break down there. In terms of dealing with storage as it goes into and out of the floodplain per se, the 1D model, the 1D unsteady model, the St. Venant equations do pick that up. And the way we've got the model built for these floodplains is we use a lot of the approximations that HE-Steady does and handles it really well, is that we use a subdivided cross-section to come up with our momentum transfer into the floodplain. So I don't know, Jeff, you can unmute your phone. If I've not hit the question, I've not addressed your question properly, let me know where I'm missing the mark.
No, I think you covered it. I was asking because we provided the Patoka Jasper site, and that one has kind of let me think, an artificial slope almost because it's a regulated site, and so we have a very rapid transition at times, especially when they're doing large releases, and so we can have storage go up very quickly, and we've been struggling to kind of capture that accurately.
Yeah. Oh, so that would explain some of this pre-peak versus the bigger peak that's later. This is hydropower or storage related releases.
Correct.
Okay. Yeah, I mean that's the thing that we've got to look at here and try to understand, and that's why we want to have a force multiplier. If we can get centers actually testing this, we give you the package. Eventually, I'm hoping that that we will have a follow-on project if what we're doing here proves successful and the program manager and program coordinator feel it's worth the funding, a follow-on project to get this into an operational sense where we've got this nice graphical user interface. It's incorporated into the typical processes, Aquarius or whatever that would be, however we decide to do that. And I could see this being like QRev, where you have this package that you can run that's even a check on your, I mean, if you don't want to use it as the primary for computing your discharge, you could run this model in concert with what you're doing with your regular stage discharge shifted rating kind of approach. See what the model gives. This may inform parts of the rating or parts of the record that we don't have a lot of discharge measurements. So anyway, I've been in the survey 34 years now, and this is one of the most exciting things I've ever been a part of. I think this really has a potential to be kind of transformative in the way we work record.
Bob, I missed a question earlier. Is it possible for DynRack to pick up on backwater with only slope for one location?
Yeah, we're uncertain about that, and that's what we would like to test for some sites that we know have backwater. I don't know that anybody from Missouri's on, but I think the Blackwater River at Blue Lick is a backwater impacted site. Anybody on from Missouri that can confirm that? I think that it may be backwater impacted. I've given them a chance to respond. Anyway, we don't know. That's why it would be helpful to have centers really kind of start testing this on a broader sense. And so if you're out there and you've got a backwater impacted site that's got observational discharge measurements, a lot of them, that's one that we would really, I think we would like to see that. We would like to test it. Okay, were there other?
Hey, Bob, this is Paul Ridland here, real quick. I think I see Tom Harris is on too, so he'll probably add to that Blackwater had some backwater at that site that I recall. But one of the things I wanted to talk about was your previous discussion there, I think when Casey brought it up about sensitivity in those 3 knobs. Have you guys actually, conducted any kind of sensitivity analysis on those that you've got out there to be able to share with folks? And then the other would be, if we're taking a look at the cross section and identifying that that's a really sensitive parameter, then how is that reconciled in terms of the floodway when we know when we have floodways that come in and that cross section is very dynamic, just with the the floodway itself having to pass through a particular channel section, we see that cross section changing. And does that impact any in terms of how you resolve that?
Yeah, we're not sure on that. So first of all, the answer to that one, Paul, is the first question is we haven't done a proper sensitivity analysis. I mean, we've got qualitative feel for that, but we haven't gone through and done a very rigorous, tweaking this and seeing kind of the percentage change on things. I mean, part of it is that you can see here, like on Blackwater or Blue Lick, even though that's backwater impacted, we've nailed the peak. At least we agree with what the water science. I say we've nailed the peak. We agree with what the Water Science Center computed in terms of the discharge. So we intend to do a more rigorous sensitivity analysis. That'll be part of the final report when we look at this. Kind of issuing this. Obviously, we've only got a little over 9 months left to get all of it done, and we're a little bit behind. We also promised in the deliverables that we would have this is taking stage data and getting a Q time series. We also promised that we would do the opposite of that. We would take a discharge time series and generate a stage. Our Weather Service partners and the National Water Model really would like to see this. We may not be able to deliver that in this particular part. I mean, we can probably deliver an algorithm. We're having a little problems with the numerical stability in the model. The numerical computations don't work as well. So we're using different numerical solvers to work on that issue. But we're not sure that we're going to be able to test it as rigorously as we'd like. So anyway, we intend to concentrate on the thing that's going to benefit the USGS the most, which is this time series of stage to time series of Q aspect, and we will do sensitivity analysis on this. Regarding your other question about the cross section, that is something we've got to play with, obviously, in the sensitivity analysis. If we've got a sand bed system like Mississippi River at St. Louis, which dramatically changes, you can see from that data, well, at least from that model that I played with back in 2015, or from that 2015 data, it nails it. And so now, is it getting off down in here? Is something where we're getting a channel aggradation on the back end of this flood wave, and so the channel's filling in, and that's why I'm departing here? We haven't teased that out. St. Louis, it's highly dynamic. It's a sand bed system, and it changes as dramatically as anywhere in the country, probably, in terms of elevation differences. So from this particular site testing, I would say that the model is a little bit insensitive to a foot or two of change in the main channel. But anyway, we haven't totally definitively said we put this to rest, but I could see that we might have a problem in certain places where you've got a highly dynamic cross-sectional geometry.
Sure. Thanks, Bob.
So Bob, this is Janice. Looking at that chart again, did you think about taking the USGS rated version and just start with like the earlier rating that's not adjusted for the discharge measurements, and then run that against both of them? The other. And see how that works. You see what I'm saying? Because this is try to maximize the data you have to check. And I also have the comment in there about that I'll follow on along this line on how to check this method and the expense it requires to collect the data to do a good job. Have you tried doing a 2D model too, to give you a set of data and that you can use for various scenarios to check against too?
Yeah, early on, Janice, that was one of your suggestions, was for us to, we have the 1D unsteady model that we used because we came up with several channel geometries to test, to basically get a first start on our algorithm development. I made the strategic decision that I didn't have time to code up a 2D model too, and we were a little concerned about all the things we were biting off. I will greatly welcome any comments. I mean, you are as much of an expert as anybody in the survey on how to test things, and so we'll connect with you on that for sure.
Okay, but there's quicker way to get those 2D models up, because I've had to do it in the past. So it depends sometimes on the model you're using, but we can talk later if we can find time. But the easy one would be to adjust the USGS rating calculation to not include that other data. That seems like a pretty simple approach to do, and then try and see how that does. I mean, it's intriguing.
So just use the base rating that the USGS had in place at the time, and don't shift it, is what you're saying.
Don't shift. Don't shift it. So it's more of an apples to apples kind of comparison.
Well, I can guarantee you that's going to be I've played around a little bit with this, but the rating had to be shifted quite a bit throughout this time.
That may be true, but see, then you get back to, for a skeptic like me who looks at this and goes, you got 3.4 and 4.0. I'm going like, well, it's going to cost more money to do this. Is it, how much am I gaining for what kind of value do I have for the improvement? Okay. But so if you make it apples to apples, you might do a better job convincing skeptics. And showing that, okay, if you only have one, I'm serious, Bob, if you have one discharge measurement, you can then show that, okay, you got a flood. You don't have to send somebody out there all through the flood potentially.
Right.
And that saves money. And that will get
on the DynRat model, you don't have to have discharge measurements at all. It just runs.
Yeah. Okay.
Yeah.
So that is what I'm saying. Because you've got good data here, you can show how well it works or doesn't.
Yeah, that's a great suggestion, Janice, and I'll do that. we will definitely do that.
We have a question. Is there any way to include tidal filtering in this model?
So this model, I don't, my gut is I have to look back at Danny Fred's write-up from 73. I think when I originally read this paper again, I originally read this back, 6 years now or so back. I don't think he meant this to be working for tidally influenced situations, simply because of the some of the simplifying assumptions he made. With that said, he did not simplify the time variant part of the equations. So maybe it would work. We just need to test it. But my gut feel is it's probably not going to work as well there. Marion, do you want to have any comment on that? You and I have talked a little bit about this.
Sure. Yeah, we did have some tidal sites in the test set that we just skipped over altogether, just because I mean, you could see the pattern, the tidal pattern in there, and one of the major underlying assumptions is the kinematic wave condition. So there's really, the flood wave, the bulk of the flood wave moves through the channel, with a nonlinear description of stage to discharge. So that's one of the things. So I don't really know how. I mean, it'd be nice to test it out more.
Yeah.
But I don't have like Bob said, my gut tells me that this isn't going to really work very well for those sites. So.
Yeah. Yeah, this is not a silver bullet for everything the USGS does, but I think it's going to be a very, very nice tool when we get done with this. Any other questions, Liz?
Not a question, but a couple comments about Blackwater River. One, it's prone to backwater and also has bypass flows and multiple ridges where measurements are made, and is 15 miles from the Missouri River.
Yeah. So it's definitely going to be a backwater potential there, being that close to the Missouri River. Okay. All right. I'm looking here. Liz, do we get all these done? I think we've addressed all the questions.
Yes, I think we got everything. Looks like Thomas Weaver sent you information on an event on the Tittabawassee that occurred this year in May when 2 upstream dams failed, and it had an atypically high flood wave.
Yeah, good. I think we may try to rerun that particular. If it's atypical, then that would be a very good test, because part of the process is that we're getting a flood wave, and we're saying all the other flood waves behave the same way. So if that's atypical, it'll be very interesting to see, especially if you guys have got some measurements during that atypical flood wave, to see how well that compares.
Hey, Bob, this is Tom. We have 4 measurements made in the 2 days near the peak. So
good. So we can compare against that. Yeah.
30,000 to 51,000 CFS. So.
Yeah. All right. I think we've basically consumed everybody's patience. So I'll give one last pause to see if there's any last questions before we end. Okay, folks, don't forget us. Again, I'll put for the last time here, I'll put the slide back up for the contact information, what we're looking for in terms of proposed new sites to test and the direct testing. So I appreciate everybody's attendance, and you guys have a great holiday.
Thanks, everybody. That's great.
Bob, you said you were going to record this. Where are you going to put the note for the recording, the link?
Looks like you missed Bob.
It does.
I'll I'll ask him. You might just send out an email to the original list of